We are recording. All right, we're live. So, just to clarify for the official record, our final exam is Tuesday, December 8th from 10:30 to 12:30. And again, it'll just be through ProctorU. And thank you, Keaton, for correcting me. I had it written down as the 10th because I looked at the schedule wrong. So thank you for saving me from myself there. So also, this Friday is a reading day. So thank you for that correction as well. So what that means is today is going to just be kind of a fun special topics day. And then Wednesday is just going to be a little bit of homework review maybe, or I guess we could do some of that today as well. And then final exam review mostly for those who need it. And then if you want to kind of meet with me and get sort of a final official say on your grade sometime, just kind of drop me an email and we can do little one-on-one sessions there. Okay, so just remember, if you've gotten good scores on all of your exams at this point, you can just take it easy and skip the final and accept your grade as it is. And if you want to take the final, we'll just take that score and overwrite your lowest homework score, or not your lowest exam score. And it's probably going to be up in the air for a lot of you. Like if I remember correctly, most of the exam scores were in kind of the C to A range. Like there weren't any like massive failures on any of the exams. So it's just going to be kind of like, you want to bring that C up to an A kind of thing, I think, for most people. But some of you did get like near perfect scores on all the exams. So you're probably good to go there as well. So yeah, just set up a time with me if you want to see your grade and decide whether or not you want to do the final. We also talked about if you want to do a little bit of extra credit, you can just write up kind of a formal lab report like you did for all the others and just pick some special interesting topic. Like if you want to make a couple of mine coupler and see if that really works, go right ahead, as long as it's a good report that shows what you did and the theory behind it and then your results, that would be great. I was thinking just make it worth, one lab. That'll be optional. Or you could do like a Wilkinson power divider, because I made a crude attempt and it failed horribly. So maybe someone can do a better job than I did with something like that. So those are some of the ideas there. And so then, yeah, I guess today we're just doing more special topics, right? Like we saw multi-conductor transmission line theory last Friday. It's not an essential theory for these classes, but it is something good to be aware of in case you ever need to go out and apply that theory in the future. You know it exists, you know what Google words to search for and what textbooks to buy when you find them. Today's special topic was mode matching, because I just think mode matching is amazing and cool. But that's about it. But it'd be interesting to see what sort of applications kind of come out of that. I was thinking about doing like another kind of special topic on something like grounding or coupling, but the references that Dr. First gave me were kind of, they were more just of like do's and don'ts rather than really any real theoretical analysis. So I've uploaded them to the files section. It'd be good to kind of download those and keep them for your records in case you're doing any sort of high-speed signal design in printed circuit boards. It's just one of those nice references to have there. But they are like 20, 30 years old. So if there's something newer out there, that would be even better, to be honest there. And I didn't feel like much of an expert on that stuff to really expound on it anyway. So that material is just there if you need it, but we're not going to like go over it here in class. So before I start showing off this idea of mode matching, now is a good time to ask questions on the homework. Just if you've been struggling on any of the problems up to this point. I think I was just saying earlier, most of the problems are going to be pretty straightforward. The hardest one is going to be what we did in Friday. So the bit where you have to plot the frequency response. So what my recommendation is, if you are struggling on that problem, go rewatch the lecture on Friday. It's uploaded on Canvas, and it kind of just goes through all the code, and all you have to do is just change a few parameters to make it work for your particular homework problem. So unless there's any major questions there on homework, I suspect most of you haven't even quite gotten around to starting it yet. I know some of you have, but there's no way anyone's going to do that over Thanksgiving. I'd be very impressed. So unless there's any burning questions, we can just jump into the mode matching method. Also, just another fun fact, I was obsessively, compulsively poking at the coupled line coupler problem over the vacation, over the break. And for some reason, I cannot get this multi-conductor transmission line simulation to really model what it's supposed to. So you see, here's the excitation line, and there's a coupler here. It's a quarter wavelength, so it's barely this tiny little sliver at 1 gigahertz. And you can see how you get a reflection out of the coupled line, the port here, and there's no transmission out through the other end, but there's still kind of a smidge of a reflection going on here, and the intensity of that coupled line is not nearly what the textbook says it should be. It should be like a value of half or 0.5 there. So I'm kind of curious about like what's going on with the theory here, because in principle, it seems like this should have matched what the theory says it should do. But when I actually do the simulation, it just kind of doesn't. So I have a lot of weird reservations about Posar's treatment of that coupled line coupler. But it'd be kind of cool, like if somebody honestly were to do this analysis and design a coupled line coupler and then build one to show that this sort of theoretical approach matches the experiment, that would probably be like an interesting research paper. Just throwing that out there. Mostly because it shortcuts a lot of the really intense three-dimensional computational simulation in order to arrive at basically the same result. So that's kind of a fun, just throwing that out there. Here we go. So let's see here. So I have this this code here written in MATLAB that draws a stepped parallel plate waveguide, right? So this is going to be an opening. So you see you have the plate separation is a 0.5 meter, and then it's going to open up to 2 meters, and then it's going to be an offset, so it's going to be symmetric. And then we're going to use like 155 modes, just because why not? And we're going to excite it with the fundamental mode from the incident waveguide here. So you just run it, you run all the calculations, and you see something kind of looks like that. So I think this is just absolutely amazing to do like full, complete solutions using nothing but closed form expressions like this. So that's why I think the mode matching method is just so cool. And it really helps to highlight just like why these modes are kind of essential in this waveguide and how you can use that mathematical framework to just kind of describe all sorts of weird, complicated systems here. So here, for example, is the Fourier series. So you're looking at the electric field profile going from the bottom here to the top. And you can see how there's the excitation right here from the incident and reflected fields. And then it just suddenly has to shoot down to 0 here. And if you zoom way in, you can see how it's not perfectly 0 because it's a finite Fourier series. So there's 155 terms in it. And as you go to infinity, these little ripples should squish away into nothing there and perfectly follow that black line there. So the black line is the incident plus the reflected field in the left hand here. The red line is the transmitted fields over here on this side. So that boundary condition where we enforce continuity is kind of what's going on here. And then if you watch the lecture, you also have to remember that not only do we have to enforce continuity on the electric field, we also have to enforce continuity on the normal derivative across here. So the derivative in that field has to be smooth across this boundary here. So you get this kind of weird shenanigan when you look at that. So again, the black curve is the magnetic field, the H field, or the normal derivative of E, immediately, you know, a teensy bit to the left of that border. And then the red curve is to the right. And it's kind of neat how that derivative doesn't really have to be 0 up here in the walls, because the tangential electric field has to be 0, but the normal component doesn't. So it can have a slope there relative to that boundary. So this is kind of the weird profile that you see again, where you're looking at the derivatives now, and the mathematics are trying desperately to match all of the fields here. So you can kind of see how it's got all that weird ripple going on there. But as you just add more and more terms, everything kind of smooths out. So a great little experiment is, let's do like just 2 modes. So you see how everything is horribly discontinuous, right? I can't enforce strong continuity with just 2 modes there. So you see some, you know, nastiness like that. So these two guys. So let's see. Let's just pause that animation real quick. So we'll just do one frame. So now we'll do maybe like 5 modes. We'll kind of move this out of the way. So now you can see how it's slowly but surely. Here, we'll kind of do this. Here, so E field on top, H field on bottom, and then you just say 6 modes. And maybe we'll do 7. It's just trying so hard. You notice it's skipping every other mode. And I think that's just because of the even symmetry here, where it struggles. So it's like every even mode is going to be 0 here. So you just kind of have to do every odd mode will actually make a change. You say 11, right? And you see as I just add more and more, it starts slowly but surely converging. So you can see how the electric field gets continuous pretty well, but the derivative gets isn't quite there. So if you zoom way in, what you'll probably see are kind of these weird little hiccups. So far away, everything looks continuous, but you zoom way in, and it's not quite. You can see kind of a little blub there at the boundary. But what we're doing now is we're just tacking on evanescent modes at this point, evanescent on top of evanescent waves. You just keep on going, 17, 27. And then at that sort of little hiccup there, it's where it really struggles with. So you have to pack on a gazillion modes. So we get up to like 50 modes, and now those little humps there start developing. All right, and then you go to 155 maybe. And then finally, it starts really. But that's funny is like once you get past like 4 or 5 modes, everything is evanescent. So you have all of these fields right there on that border that we're trying to enforce continuity, but they have like no propagation at all longitudinally. It's like they just decay over like 2 or 3 grid pixels, especially when you go up in like hundreds of modes. They contribute nothing at all whatsoever to the fields out here. They only help to kind of enforce that continuity in the local little range right there at that boundary. So in practice, if all I care about is like how much power is actually propagating across this border, you don't need to calculate things out to hundreds of modes, just because all the evanescent modes aren't really carrying any real energy there. So there's some fun stuff there. So that's kind of the idea of mode matching in a nutshell. So here's another one where we can do a constricted waveguide. Give that a second to crunch on the numbers. So here's a good example there. So now you have a wave coming in, and there's all these reflections here. So there's much more a strong reflection in a system like this. And then that you can see how, because everything's all asymmetric, the waves are struggling to kind of get up into that other target waveguide. So you can do a lot of really fun stuff with this kind of method. And it's just really, really complicated, exotic Fourier series calculations there. But again, you can see here's like the continuity of your H field, the continuity on your E field there. And as long as you're enforcing those boundary conditions, then you've got a correct answer there. So that's pretty neat stuff as well. And plus it just makes really awesome psychedelic pictures when you do it. That's my favorite part. And just let that go. This would make like a great screensaver, I think. But I love kind of seeing how that blob of energy is like creeping around the that little step there, which is pretty neat. So that's the mode matching method in a nutshell. And again, like I said in the lecture, you can do a lot of really neat stuff with that. Like you can do waveguide apertures, you can do like waveguides, you can do like a 90-degree bend with that sort of thing. And it's just enforcing that same continuity at all of the boundaries, and then all the internal fields just have to follow that parallel plate formalism. All right, so if there are no other questions on that, then we could just kind of jump into the homework and kind of look over the problems. Like I said in the lecture, you're not really expected to do anything with something like that. That's pretty computationally intense. But just knowing that it's there, that it has some interesting applications is very interesting. or it can be useful to some, depending on what you do for your careers later. Let's see, I think we're on problem set number 9. Yeah, there we go. So yeah, I guess we can just walk through kind of the homework problems here. And then Wednesday will just be like final exam review. So I'll be sure to write the final exam between now and then, so I have a sense of what all the material will be. And then we'll just kind of do a lot of broad overview of the various materials. And we'll kind of go use that as a springboard to answer questions and give you a sense of what the final will be like. So we start off, design a Wilkinson power divider. And remember, we did this exact same problem in class. Let's see. So 2.4 gigahertz, use a microstrip. So we're using our microstrip parameters here with a phase velocity 0.55 c. So given some characteristic impedance, what is the width of that microstrip? So let me pull up kind of a blank MATLAB window here. Oops. Somewhere around here I have, there we go. So today is the 30th, there we go. There we go, okay. So we'll go ahead and do a screen share like that. And you see my code here? Yeah, okay, we got that. Okay, so we'll start with just kind of inserting our parameters. Let's see, so we had F naught was 2.4 gigahertz, D naught is 75 ohms, and our phase velocity, 0.55 times the speed of light. We said W was, oh, we don't know what that is yet, that's a question mark. 1.56 millimeters for the height on the microstrip. And our, okay, 4.6 there. So I don't actually need those values there. So first things first, let's open up our lab code again. Is it? Nope, not that. This was it. There we go. So that same little, just using those closed form expressions. And let's see, so here is the characteristic impedance as a function of the strip width. So I've got 4.6 here, and I think we put D should be 1.6 millimeter. And then it just calculates the impedance. And then I need, there we go, I just need 75 ohm. So that's that little intersection point there. So we've done this before. And so we should know from long ago that about 1.37-ish is my W, right? So just from the curve fit, 1.37 millimeters. So there's the answer there. So we got 75 ohms. Here's the W I need to get. So calculate the characteristic impedance of the quarter wave line. So remember, for the Wilkinson power divider, quarter wave line, we did this in class before. There's a square root of 2 in there. Does anyone remember if you multiply or divide? I think for the Wilkinson, you have to multiply. Yeah. Yeah, because when you put them in parallel, they're supposed to divide out and give you a match. Okay, then, so that's just what strip width do I need for that? So again, we just go, okay, what is that value? Actually, I don't even need that. We can just go back in. I actually already kind of had that code. You just do another little horizontal bar, oops, where you put in 75 and 75 times square root of 2. And it's off the chart there. So I got to change this a little bit. Let's go down to 0.5. Let's see, where is that going to be? Is that just sort of like squeezing off the chart? Oh, yeah, it's way up there. Okay. It's just my axes aren't really showing. There we go. Let's do something like that. Oh, sorry, not that. There we go. There. It's just falling off the edge there. So you notice as you get very high impedance, you got to really squish those traces down a bit in this case. So you see it's about a half a millimeter, 0.57. So then you just come back and you say, okay, so that's W1, we'll say. W2 is going to be like 0.57 millimeter. So like a half a millimeter for that really high impedance there. So that's the quarter wave line. And then what resistor, you just multiply by 2. So that is 75 times 2 is 150. And then the length is the final little bit. So there's going to be some center frequency. And so the way that works is, what's my wavelength? So lambda is frequency over phase velocity. And then you just say, calculate quarter wave line length, all right? So just L is lambda over 4, like that. Which in this case, you get something, whoops, I made a mistake. It's phase velocity over frequency. That was wrong. Nope, that's not it either. What's going on? Oh, my, that's what's going on. There it is. Now I'm getting a sensible number. I was getting like 10 to the 50th, 10 to 16 meters out of that. Because that was off by 18 orders there. So you get something like, what is that, 7-ish centimeter? I'll let you figure out the details when you put that into your into your answers. So that's the length. And then the frequency response is kind of the final tricky part. So did we do this in class? I don't think we quite did this in class. So this one's going to be a little tricky because we're going to say calculate frequency response. I forget if we did this in class or not. I know we did it for the other guy, the coupler, but no, I don't think we did it quite for the Wilkinson. So we'll just kind of do it again. So we'll just go from, say, 0 to 6 gigahertz with 1,000 samples, right? So we'll just say N is 1,000. So we're going, from 0 to 5 gigahertz, and then we truncate there. Okay. So you just go 0, 5 gigahertz. And then the question is, what is the parallel, the equivalent input impedance looking down that Wilkinson power divider? So what you have is a parallel combination of 2 lines, and each one has, a quote unquote load of 50 ohms at the end. So as you change frequency, it's as if the electrical length of those lines is just going to change. So we'll just loop over frequency and calculate gamma, basically. So we'll just say gamma is, you have to instantiate it with something. So do something like that. And you go 4, and it's just 1 to n. We'll pluck out our frequency here. And then the question is, so you say calculate input impedance down the Wilkinson line, I guess, or leg, because there's two of these. So we're gonna do, but they're the same, so they're just gonna be in parallel or divide by 2. So you just say Z in. It's going to be our transmission line input impedance again, our favorite equation. So just to remind ourselves what all the parameters are. So I like to just copy the function declaration so I know what all the little bits are supposed to be. So the frequency is going to be our nth frequency here. That L is a fixed constant. The load is actually Z naught. And then the Z naught is actually ZQ. So this is the characteristic impedance of the line, and that's the load at the end there. And then you calculate the parallel combination of each leg of the divider, right? So you just say Z equivalent is divide by 2 because they're symmetric and they're in parallel. So then finally, gamma of n is Z equivalent minus Z naught divided by ZQ plus Z naught there. Then we finally will just calculate return loss. RL is 20 times log 10 of the absolute value of gamma. And then plot results. You say figure 1, we'll clear it. You just say plot frequency in gigahertz, return loss, and make it black. And we'll fix our axes here. So it's going to be 0, max value, and then -40, 0, like that. Bloop, and there you go. So there's the frequency response of a Wilkinson power divider. You can see how it's perfectly matched right there at 2.4 gigahertz. And so what's neat about doing a code like this is someone could come along and say, oh, that's great, but I need one that is matched at 1.8 gigahertz, say. So all you have to do is just change that variable, and the rest of it all will just crunch right on out. And now you can just play with every little knob available here. 2.4. Or I could say, what if it happens if I change it to 50 ohms instead of 75? Will that have any major impact? So if I say 50 and then 75, you notice it didn't really change anything. So the actual value of the characteristic impedance doesn't change the frequency response. Okay. So that's the basic gist there. So then label your axes, and there's your return loss. And then finally, how are we doing? Oh, we might have just enough time to do the rest of these. Yeah, so this stuff here at the end, by the way, it says design a coupled line coupler. So I have all these reservations about the theory in the book, but so that's why I don't go into too much depth. I just say follow a few equations from the book, because I'm not sure if I'm just failing to simulate this correctly or if there's something genuinely wrong with how the book explains it. So we do a little bit of token treatment at the end, but that's just plugging in a few equations out of the text. So that's pretty straightforward. The difficult part is going to be plotting the frequency response of this coupler here. So this is everything. We basically did this in class on Friday. Or was it Friday? Not Friday. It was Friday. It was a holiday. It was last Wednesday, I think we did this. So design the quadrature hybrid out of microstrip, assuming the same parameters as before. Okay. So you just do something like that. So again, you know that W1 is the same, but W2, we need to, it's a different characteristic impedance there. So before with the Wilkinson divider, the legs split and they were multiplied by square root of 2. In the quadrature hybrid, they divide by square root of 2. So I'm going to divide ZQ is equal to Z naught over square root of 2. Like that. So we'll call this Q, I guess, for that little quarter wave segment again. And this is going to be z naught over square root of 2. There we go. So you just take off the semicolon, and that turns out to be about 53-ish ohms. So you can kind of fill in the blank later. So then now we have to go back to that that curve fit again. I accidentally closed the tab, so give me a sec. So I really should have written just my own separate function because we keep coming back to this. So we'll do a divide there instead of a multiply. And so you can see, since it's really close to 50 ohms, so you notice it's about 2.7. There you go. 2.7 millimeters. Yeah, that makes good sense. So what we'll get is about 2.7 millimeters, something like that. Right around 53-ish ohms there. Okay, so there's the characteristic impedance for those top and bottom segments. The left and right are still just Z naught, so they don't change at all. Calculate the width. How long should the segments be? So they're still quarter wavelengths, same center frequency, so that doesn't change. And then finally, we have to plot another frequency response. So this is that whole ABCD matrix idea again. So this is where it gets a little, this is the tricky part, right? So plot frequency response of insertion, not insertion loss, return loss. So again, so I give the same 0 to 5 gigahertz. Yep. So this hasn't changed. So I can actually just recycle some variables over here. That we'll have to set that to a bunch of zeros again. And then we're going to do the same sort of frequency response issue. So here we go. So this is, again, going to be the tricky part. So what we have to do is that whole ABCD matrix thing. So calculate ABCD matrix for even and odd modes of excitation. So so we did this all, and I wrote it all down. So now we're just going to kind of go back to the notes from class the other day. Or I can try and do this from memory. So here, let's. So remember again what is happening here. So I'm gonna stop sharing and go back to the camera here. So the quadrature hybrid. Let's kind of just whip out the pictures here. There we go. So this picture here is very helpful for that, where you have the even mode here, and you can see how you get the little 1/8 of a wavelength segment here with the open circuit. Because if I'm exciting it with the same voltage here, no current is going to flow across that boundary there. So it's as if it's an open current, open circuit. And same thing with the odd mode. I have plus and minus. Now this is going to behave like a short circuit, as if it has 0 volts, because again of the symmetry. So that's where this whole grounding thing is coming from. And then you imagine exciting both of these simultaneously, where the two halves here come together to give me 1 volt at port 1, and then the plus and minus come together to give me 0 at port 2. So an excitation of a single voltage along port 1 is a linear superposition of these two events happening simultaneously. So you just calculate the one and you calculate the other, and then you just add their results together. That's the idea. You know, and the book even kind of gives you this little expression here. So the reflection coefficient coming out of my port is just the 1/2 times the even plus 1/2 times the odd. And that's because you're exciting them with 1/2. You basically get that idea. Okay, so half my voltage is reflected by the even mode and the other half comes out of the odd. So you have to calculate the even and odd reflection coefficients, which basically says you look at this system here, calculate its reflection coefficient, calculate that one, and calculate, which gives you the odd reflection coefficient there. So that's sort of intuitively what's going on. So we'll draw out the even mode here, where you have this guy here. So again, this is my Z naught out here, which is 75 ohms. Coming in here is my Z naught. This is Z naught over square root of 2, and it is a quarter wavelength. Well, technically that's a quarter wave. It's a fixed length of line L, which I've chosen to be a quarter wavelength at some particular frequency. And then this here is L over 2, and then that is L over 2, like that. So that's the even mode there. So you write that out as an ABCD cascade. So there's 1, 2, and 3, and incidentally, 1 and 3 are identical because they represent the shunt stubs. And then 2 here is a series length of line with some load at the end. And then for the odd mode, you just kind of draw it out again. So everything's the same. The only difference now is this has to become 0 volts here at the end of that guy. And everything else about it is the same. So that again becomes a cascade. 1, 2, and 3. Ooh, 3, sorry, I'm getting a little sloppy. And instead of open circuit here for these shunts, these become short. So that changes these guys over here. But then the idea is that it's going to be the same because I have, so we'll call that like M1, M2, and M3. Say, so my entire ABCD matrix for this entire cascade is just M1 times M2 times M3. So you have to calculate each one of these at each frequency and loop over all the frequencies. So we'll see how far I can get before we run out of time. And again, remember, this was in class and the recording is uploaded. The only major difference, I think, is I picked a different frequency and a different characteristic impedance. So if you followed along then, this should just be review here. So let's go back to sharing. Let's see, even mode ABCD matrices. So number 1 is a shunt stub with length L over 2. And open load is what we're interested in. So what we're going to do is, so you look at, again, where's our table in the book? There we go. So table 4.1. So we'll make a little note here. Consult table 4.1 for ABCD matrix elements. Page 190. So a shunt stub length L over 2. So what do we get? We get A is equal to 1, B equal to 0, C is this Y term, and then D is going to be 1 again. So the question is, what is this term here? So Y is 1 over the impedance, the equivalent impedance looking in, and then my impedance looking in is going to be my transmission line input impedance looking down that length of that stub. So we'll do that. So it had the characteristic impedance of that line is going to be Z naught. The load is going to be an open circuit, and its length is L over 2, like that. So that's pretty straightforward there. So that tells me the admittance of that thing. Then the second guy I'm going to need is a series line with length L. And the load, quote unquote, doesn't matter when you're doing the ABCDs here. So you have to calculate that beta L is going to be, so what's my beta? It's you got to calculate your wave number at each given point. So beta is it's omega over c, so 2 times pi times fn divided by the phase velocity. And beta L is just beta times L. There we go. And we can kind of skip a little bit. We'll just put that together into one line. There we go. Call that beta times L. Nice to make that a little shorter. So we need, that's the electrical length. It has units of radians. And just to make sure everything is unambiguous, it helps to put parentheses in like that so you don't get confused. And then you calculate the, so let's just do this. A, B, C, D, stub. Got to build a matrix here. A, B, C, and D, like that. So I need to use those variables again. So A is cosine of beta L, and B is 1j times Z naught times sine of beta L. C is equal to J times 1 over Z naught times sine of beta L. And then D is cosine beta L. So A. Yeah. So you say A, B, C, D of line. It's going to just be A, B, and C, D again, like that. So we're just going to go through the even, and we probably won't have time to do the odd. But remember, for the odd, everything basically is the same. You just would replace that little term with a 0. And then all the rest of the analysis follows the same trend. So we'll just say A, B, C, D. Even is A, B, C, D of the stub times A, B, C, D of my line, and then times of the stub again, like that. Okay. So now I have to repeat for odd. So the whole analysis is going to be the same. In fact, all I have to do is change just this guy. Just put in a 0 here, because that line length shouldn't change. So that guy is fixed, whether or not we're in the even or odd mode, isn't it? So then you just do this, odd, and yeah. So we changed the stub, putting 0 in for the load instead of an open circuit. Everything else is the same, so we can just leave that matrix there the same as before. Okay, so then the tricky part, let's go back to just double check the book. There we are. So I have to convert that into, convert A, B, C, D matrices into S matrices. So this was something that started happening enough that I just went ahead and wrote my own script for it, my own little function. So A, B, C, D to, is that right? Oop, that's not what I meant. There it is. So I wrote a function just as A, B, C, D to S matrix. Because if this is a conversion that you find yourself having to do a lot, just write a function for it so you don't have to keep copying and pasting all of this stuff here. So you see, you give it an A, B, C, D and a Z naught, and it returns an S matrix. And it just follows the table 4.2 using that conversion equation there. So that is super handy to just write something like that for yourself. So you just say something like SE for the even. And then we'll get an odd, just like that. And you just put in the odd there. So then we need to unpack the reflection. Oh, I might just barely finish in time. So gamma even is just S11. Boop. In fact, I'm just going to call that GE for simplicity. GO. And then finally, gamma is 1/2 of the sum, GE plus GO, like that. So that is equation 7.62. And then if you want to do transmission coefficients and all that other fun stuff, you just unpack different, oop, that should be an odd. There we go. Okay, then we'll just go ahead and plot that. We should see something very similar, almost exactly what we had last time. So we'll calculate my return loss. There we go. And that's it. We should see, whoop, did I make a mistake? I might have made a mistake somewhere. Because there's my Wilkinson, and this guy is being weird. So what happened there? Oh, I did a dumb thing. That should be gamma of n. There. I was just overriding it with a single value there. So there's my frequencies. Oh, okay. So it looks like I made a mistake somewhere. That's not quite what it should look like. So I thought I was following the same procedure as last time, but it looks like I may have inserted a mistake somewhere. Does anyone know where it is? Who was actually following along? I swear I was just following this along and following the same procedure. But I probably made a typo in there somewhere. Where did I mess up? Cosine, cosine, yeah, beta times L. Oh, we can just pull out our code from last time there and see what we missed. So I think we did this on the 25th. So I thought I was just following that along. Okay, that's the mistake. So let's close some of that. So when you're looking, no, wait, is that right? Yeah, so that series length has a different impedance. And there it goes. So don't forget, your series length of line has an impedance of that quarter wavelength, that square root of 2 thing. I put a Z naught there, which was wrong. All right, and then you'll see that exact same, you know, that is a very characteristic shape that won't change with the characteristic impedance. Everything's sort of just normalized out in terms of reflection coefficients and ratios there. Okay. So that's basically it. There's your answer for all of the homework problems. I just basically went through them all. And the last two are just plugging in equations from the textbook here. So a coupled line coupler. So that is going to be, where is that? That's going to be section 7.6. So really all you have to do there is apply equation, let's see, calculate the characteristic impedance of even, and then the odd mode. So you look at equation 781, tells you, or 781 and 782. So you have to solve those for your even and your odds. And you also know that the product of those guys is going to be 50 ohms. So assume 50 ohm characteristic or 75 ohm characteristic impedance here. I didn't say specifically, but I should have said assume the same parameters as before. Yeah, so 75, I should have specified 75 ohms again is what you're after. All right. So any other questions? That's all I have for today. So you just look at, yeah, equation 777, and then equation 781, I think is all you need. And you should be able to, oh no, it's 787, 787b does it for you right there. That's the solution. So it's right there on page 355. So just a little bit of token treatment of it. But like I said, I'm too scared to go into too much depth on this because I don't know how much I trust this theory. Okay, so any last minute questions before we call it a day? And then come Wednesday, it will just be kind of a final exam review because that was the homework. Okay? And if there are no questions, we'll go ahead and stop the recording.